Laboratory 8. The aim of this laboratory is to perform exactly the same work that's been done previously. However, we're going to redesign our circuit. You should be very familiar with this circuit, the differential amplifier. We've found the gain is easily calculable from the values of our collector load resistance and our emitter resistance. Our emitter resistance will be a function of the tail current. You probably found a value of common mode rejection ratio from the previous lab, ballpark 40-50 dBs. We're now going to improve that. If we look at Figure 1, we're going to build a beta helper current reference cell and then put a current mirror in the outputs of the two differentials on our circuit. So your work to do is to design the current mirror to support the design, and then you possibly use the same design parameters that you gathered before in Lab 7. Doing so will now give you a complicated design. Again, please don't change the values or the design of the supply source, 10 millivolts input signal, or the DC bias. Let's have a look at our design. Okay. Okay, so number one, I don't want you to adjust the DC bias. We're going to keep the DC bias as 1 volt. Okay, so that means these two signals here are sat on a DC level of 1 volt. So if we have our voltage signal here, and we have minus VEE down the bottom, and we have VCC at the top, so this is 10 volts. Okay, and down here we have minus 10 volts. In the middle we've got 0. Somewhere around here we have 1 volt DC. Okay, that is our input bias level. We then have an AC source, which is very low magnitude, so not to scale. We have a sine wave coming in at that point to our differential. Of course, we're going to have, what's going on with my pen tablet? We're going to have our antiphase sinusoid signal as well. Okay, so leave these parameters alone, they are part of the design spec. This is the new circuit. As you can see, this design is exactly what you built last week, and this design is a copy of that design, but we're looking specifically at the common mode signals coming in to the input and the common mode signals coming out. So we're looking specifically at those designs. So in our differential design, the piece of work that we're really going to do now is we're going to design this current source, and we're going to call it I-tail. This one here is an exact copy. It's the same thing. That's I-tail again. Okay. Our design parameters start off with VCC. You'll build your Kirchhoff's voltage loop around this system. This effectively will be our reference resistance. This transistor is feeding base currents into all three devices, and this one is our reference VBE value. Down the bottom we have emitter degeneration. I'm not going to tell you how to design that. You should know how to design that, and you should know all the equations. If you're designing to the previous specification, this value, the tail current, is 2 milliamps. In the laboratory spec, I've said I want 2 milliamps for both circuits, and I've suggested that the reference line should be 1 milliamp, approximately. Remember, we're going to make this an approximation. As there are two outputs in this case, what I would do in my design parameters, I would make sure this is perfect, okay, exactly 1 milliamp, and then I would make this close to 2 milliamps, and then I would optimize this component down the bottom. And then I would do the same thing over here. So I'm going to make this perfectly 1 milli, and then this perfectly 2 milli, and this one perfectly 2 milli. That's my design parameters. Okay, I'm not going to cover anything else. I think you should be able to do it completely by yourself now.